After watching this video, you'll be able to describe the problems with the waterfall method and describe the typical relationship between software development and operations prior to DevOps. It's important to understand what brought us to DevOps in order to fully appreciate the problem that it solves. Architects would spend months and months designing the system on paper. Creating requirements documents, creating design documents, making high-level designs, low-level designs, system-level designs. Then finally, we get to the development phase, where development worked for months and months on features in an isolated development environment. As they developed the code, if the designs are wrong, it was very expensive to go back to the architects. Once we developed all the code, we'd get to the testing phase, and we'd test all the code at once, and testing would open defects, send the code back to development until no more severity 1 or 2 defects were found. At some point, development would release the code to operations for deployment. This release to deployment would happen several months after the code was written, maybe even a year later. Some of these projects took up to 2 years. Then the operations team would take what seemed like forever to deploy it because they had no idea what the developers had built. And operations team kept running it from that point on. We call this way of working the waterfall method. With waterfall, everything happens in phases. Requirements are gathered and a requirements document is generated. Then that phase ends. The artifacts for that phase flow down to the next one. In the next phase, we do all the design, and the design is documented in high-level designs, low-level designs, system-level designs, and that phase ends. Those artifacts get passed down to the next phase, and the coding begins, where developers take those low-level designs, the design documents, and write the code that implements those designs. There are entrance and exit criteria to each of the phases. So all along, we're coding in isolation. We're not integrating my module with the next person's module. Finally, you get to the integration phase when all those modules come together. This is the first time we realize we don't know whether all these pieces even work together. And then we move on to the testing phase, because now we've got a system that people can test. And as they find bugs, they must go swim back up the waterfall and open some bugs in the coding phase and do some recoding. Finally, after all that testing, we deploy the software. It's called waterfall because if there's a problem, it's very hard to go back, like trying to swim up a waterfall. You have to go all the way back to the design phase. In fact, because we treat software development like civil engineering projects, sometimes those designs have moved on, right? The architects moved on, the designers moved on to the next project, and you've got to go find them and get them to change the design. Then you get the developers to change the code in hopes that it integrates this time. This process was very error-prone, and there was no room for making changes late in the process. You didn't know whether it worked until the end, so it was very high risk. But we developed software like this for years. So what's wrong with this approach? Well, there's no provision for change. Every phase has entrance and exit criteria. When one phase ends, the next one begins. And there's just no provision for going back and changing the design or changing the requirements or anything like that. Another problem is you don't know if it works until the end. There is no intermediate delivery. Nothing is delivered until that last step when we give it to the operations team and say, go deliver the thing to production. In addition, with each phase, there are issues that are just passed down. And of course, every one of these is an opportunity to lose information and to have a mishap. People get blocked because they can't accept the work from the previous phase, and then the next phase is delayed. Mistakes that are found later are very, very costly. It's especially costly to find something that's designed wrong in a testing phase and then go all the way back and redesign it. Finally, these delays create long lead times between deliveries. Also, the overall problem with Waterfall is that the teams are working separately. They're unaware of their impact on each other. Designers are unaware of the impact of the code. The coders are unaware of the impact on testing or impact on integration before we get all the code together. So everybody's working in their silos for their phase. And the scariest thought is that the people who are furthest away from the code, the poor operations team, have to deploy it and run it and manage it in production. They know the least about the code, and they're the ones expected to run it. In this video, you learn that traditional waterfall development creates problems such as delays, frustration, long lead times, expensive late changes, and operations managing unfamiliar code. And that in the past, software developers and operations worked in silos rather than working together. After watching this video, you'll be able to describe how extreme programming was the beginning of Agile and describe Agile and how it became part of DevOps. In 1996, Kent Beck came along with extreme programming. Kent based this on an iterative approach. He described these feedback loops. Release plans take months, iteration plans take weeks, acceptance plan takes days, stand-up meetings are conducted every day, and pair negotiations are done every hour, and unit testing in minutes and programming in seconds. These tighter and tighter loops represent the approach. The idea was to improve software quality and get feedback quickly, get something out to the customer, get feedback quickly, and then iterate on it. Extreme programming was intended to improve software quality and responsiveness to changing customer requirements. It emphasized concepts like pair programming. I encourage you to try pair programming. It gets two sets of eyes on every line of code and helps cross-train your team with skills. For example, a person who really knows Python will pair with one who's just learning Python. And they work together, and the junior programmer gets to see how the senior programmer approaches the problem. Pair programming is a great way of mixing the skills in your team and getting everyone under the same code to understand it at the same time. Kent Beck's extreme programming was one of the first Agile methods. In 2001, 17 software developers met Agile methods. In 2001, 17 software developers met in a resort in Snowbird, Utah to discuss these lightweight development methods. What they came up with is called the Agile Manifesto. The Agile Manifesto emphasized valuing individuals and interactions over process and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. That is to say, while this valued the items on the right, we value the items on the left more. It was a big breakthrough. People began to change their organizations to be agile. people began to change their organization to be agile. In agile development, requirements and solutions evolve through a collaborative effort of self-organizing cross-functional teams and their customers. It advocates adaptive planning, evolutionary development, and early delivery, and continual improvement. It also encourages rapid and flexible response to change. Work is done in increments called sprints. Planning is adaptive. We plan for the next 2 weeks, and then the 2 weeks after that, and then the 2 weeks after that. Agile includes continuous improvement that is asking what you learned and what you're going to do to change. The devs were latching onto it, and I was in a couple of agile teams back then, and it was really working out well. But being agile doesn't solve all the problems. There are still ops to consider. And agile was in direct opposition to the way operations was being measured. I was on a project that illustrates this concept. We started the project in January. Toward the end of February, we had code we actually wanted to deploy. We went to the ops team to deploy it, and they said, open a ticket. So we opened a ticket to get 3 VMs. And a couple days later, we asked about the VMs. It takes 20 minutes to make a VM. And the ops team said, it takes 2 weeks to find a person who has the 20 minutes to make the VM. The ticket sat, and then it was kicked back. The project was deployed in September, and I left the project in December. I couldn't take it. It was crazy that the developers are being agile, working in sprints, and then waiting for the ops team to deploy something. Agile alone is not good enough. Patrick Dubois had the realization that we need to make ops people agile. The result of this situation is called two-speed IT. Here's how it works, or rather doesn't work. A developer needs some resources. Ops tells him, submit a ticket. The developer says, never mind, I'll go to the cloud. And the developer goes to the cloud and gets the resource immediately instead of waiting for days for his IT organization or service a ticket. This is the slow speed of going through the company resources and the fast speed of getting resources outside the company. This is how shadow IT gets started. There are resources that the business doesn't know about because people go around the IT shop because IT is not meeting their needs. Then the cloud makes this very easy to do, and I would bet that every organization has users with cloud accounts and no one IT knows about. We need a solution to this problem, and DevOps is an answer. In this video, you learn that extreme programming paved the way for agile development, and agile emphasizes valuing individuals, collaboration, responding to change, adaptive planning, early delivery, and continuous improvement. After watching this video, you'll be able to list key examples of DevOps growth that occurred from 2007 to 2019 and summarize the contributions of key influential people in the growth of DevOps. I'd like to take you through a brief history of some significant events in the early DevOps movement and point out who the key influencers were. DevOps really started in 2007 when Patrick Dubois recognized that Dev and Ops weren't working well together. He wondered if there was a better way. The next year, at the 2008 Agile Conference, Andrew Clay Shafer created a Birds of a Feather meeting to talk about agile infrastructure. Shafer didn't think anybody would come, so he did not show up to his own meeting. Patrick Dubois showed up, and Patrick went to looking for Andrew because he wanted to talk about agile infrastructure being a solution to get operations to be as agile like the developers were. This is where DevOps got started. Then in 2009, at the Velocity Conference, John Allspaw gave a talk about 10 plus deploys per day, Dev and Ops cooperation at Flickr, and the idea started gaining traction. This talk made people take notice of what was possible by adopting these early DevOps practices. Also in October 2009, Patrick Dubois, often called the father of DevOps, held the first DevOps Days conference in Ghent, Belgium. It was described as the conference that brings development and operations together. This is where the term DevOps was first used. DevOps Days is now a local conference held internationally several times a year in different cities. In 2010, Jez Humble and Dave Farley wrote the groundbreaking book called Continuous Delivery that sets out the principles and technical practices that enable rapid, incremental delivery of high-quality, valuable new functionality to users using a technique called continuous delivery. Through automation of the build, deploy, and test process, along with improved collaboration between developers, testers, operations, delivery teams can release changes in a matter of hours, sometimes even minutes, no matter the size of the project or the complexity. This book is over 10 years old, but it still has a lot of great concepts that help change a lot of people's thinking about how to perform software delivery in a continuous fashion. In 2013, Gene Kim, along with Kevin Bear and George Spafford, published The Phoenix Project, a book based on Elijah Goldratt's book, The Goal. The Goal is about a manufacturing plant that is about to go under and what they had to do to bring it back to life. It's a story about lean manufacturing principles. The Phoenix Project is about an information technology shop in a company that's about to go under and what it took to bring it back to life. This story is about applying lean manufacturing principles to software development and delivery. In 2015, Dr. Nicole Forsgren, Gene Kim, and Jez Humble founded a startup called DORA, DevOps Research and Assessment, that produced what are now the largest DevOps studies to date, called the State of DevOps Report. Nicole was a CEO and is an incredible statistician, and through this research, she found that taking an experimental approach to product development can improve your IT and organizational performance, and that high-performing organizations are decisively outperforming their lower-performing peers in terms of throughput. The research shows that undertaking a technology transformation initiative can produce sizable cost savings in any organization. If you haven't read this year's State of DevOps report, I strongly urge you to do so. The DevOps Handbook was published in 2016. It was written by Gene Kim, Jez Humble, Patrick Dubois, and John Willis as a follow-on to the Phoenix Project, and it serves as a practical guide on how to implement the concepts that were introduced in that book. John Willis, by the way, worked at Docker and Chef back then and is a DevOps Days coordinator after being at the original DevOps Days in Ghent 2009 with Patrick Dubois. If you only read one DevOps book, this is the book to read. They look at companies that have adopted DevOps and document what did work and what did not work. It's a great read. Over the past 10 years, there have been 40 DevOps Days events in 21 countries, and it's growing. Patrick Dubois was the lead for DevOps Days from its inception in 2009 until 2015, and then Bridget Krumhout became the lead in 2015. She's also a co-host on a very popular podcast, Arrested DevOps. If you don't listen to it, you should. I've learned a lot from listening to Bridget. She's heavily involved with the DevOps community. She stepped down in 2020, but stayed on the advisory board of DevOps Days, and it is a great event. I got to attend DevOps Days in New York City in March of 2020, and I loved every minute of it. These are some of the major influential people in the early DevOps movement: Patrick Dubois, Andrew Clay Shafer, John Allspaw, Jez Humble, Gene Kim, John Willis, Bridget Krumhout, and Nicole Forsgren. They weren't the only ones, but they went out and made a difference. They showed us how DevOps can be impactful. They explained that it's all about changing culture, not just about tools. They explored measurements and the idea of changing how you work. These are the early pioneers. Why is this history important? It's important because DevOps was a grassroots effort started by people like Patrick Dubois, who just wanted to eliminate the roadblocks in software delivery and figure out how can development and operations work better together. Damon Edwards, who co-hosted a podcast with John Willis called The DevOps Cafe, said it best in his talk on the short history of DevOps way back in 2012. DevOps is from the practitioners by practitioners. It's not a product, a specification, or a job title. It's an experience-based movement that is decentralized and open to all. People were beginning to realize that DevOps was a better way to work. In this video, you learned that Patrick Dubois started the DevOps movement in 2007 with a simple idea of getting development and operations to work better together. DevOps grew through the efforts of influential people such as Patrick Dubois, Andrew Schaefer, John Allspaw, Nicole Forsgren, Bridget Krumhout, Jez Humble, Gene Kim, and John Willis. After watching this video, you'll be able to describe social coding principles and recognize how pair programming creates better code and better programmers. What is social coding? I like to call it open source for inner source. Social coding is something that the open source community has been doing for years. What's new is bringing these concepts into the enterprise and coding as a community on internal projects. In the past, developers worked in private repositories, and you had to be a member of the team to contribute. Everything was controlled by access control lists and a strict need-to-know basis. The problem with that is no one knows you're working on it. So there's no possibility of reusing code because no one even knows it exists. So enterprises continually reinvent the wheel because no one knows the wheel has already been built. With social coding, repositories are public, and everyone's encouraged to fork the code and contribute. This is a hugely different way of thinking. Development teams love to think, this is my code, no one else can touch it, but they need to get over that for the good of the company. You would think that anarchy would ensue, but actually it works quite well because it's controlled by the repository owner. The person who owns the repository is still in complete control of the contributions. What problem is social coding solving? Well, let's say you see a component. It's solving, well, let's know the contributions. What problem is social coding solving? Well, let's say you owns the repository is still in complete control of the contributions. What problem is social coding solving? Well, let's say you see a component. It's 80% of what you need, but there's some missing features. How do you add those missing features? You now have a decision to make. Do you make a feature request to the repo owner for a new feature and risk that your request will be at the bottom of their priority list, or worse, their funding gets cut and your request will be cut out first? Or do you rebuild 100% of the code just to get the 20% that you need, so as not to have a dependency on another team? It's sad to report, but many teams select the latter and reinvent the entire wheel just to get the functionality they need. This is a huge waste of resources for any company, but it happens all the time. So how does adopting social coding principles solve this? Well, you discuss a new feature with a repo owner and you agree to develop it for them. This allows you to leverage everything that they've done and add the feature that you need. You open up a GitHub issue and you assign it to yourself so everyone knows you're working on it. Then you fork the repo, create a branch, make your changes. When you're all done, you have something to contribute back. Well, then you issue a pull request and signaling that you're ready for review. The repo owner can decide whether to merge your code back into the main project. The repo owners are in full control. They can ask for changes because they do the merge. They can ask you to write more test cases if you don't have adequate test coverage. They treat you and your contribution like any other member of the team. This is a win-win situation. You get to leverage another team's code and all the functionality that you need. And the other team gets a feature added for free. The company saves money because code is being reused instead of rewritten, and everyone is happy. This is how open source works, and this is how companies should treat their inner source. Pair programming is an aspect of social coding that is taken from extreme programming. It consists of two programmers sharing a single workstation, one screen, one keyboard and mouse between the pair. The programmer at the keyboard is usually called the driver. The other programmer, also actively involved in programming tasks but focused more on overall direction, is called the navigator. While the driver is typing, the navigator is checking their work, or perhaps looking something up, or thinking about what's coming next. Then after about 20 minutes, they swap roles. This way both get to play each role. I pair program whenever I can at work. I like this aspect of social coding. One of my personal weaknesses is that I'll agonize over what to call a new variable function. I want to get it perfect, to make the code as readable as possible. Having someone else to bounce ideas off of helps me make those decisions faster. You might think that pair program is using twice the resources to get the same amount of work, but it's not like that. There are many benefits of pair programming. The first benefit is higher code quality. There's something about programming out loud that leads to clearer understanding of the code. In the past, when I wrote code, I wrote it alone, and then I explained it to someone, I would pick up on a bug as I was talking out loud. Like, I didn't see the bug when I was looking over the code in my head, but I saw it as I talked out loud. Having to explain code to someone forces clarity. This means that defects are found earlier, and that's a good thing because it lowers the maintenance cost right down the line. The later a defect is found in the process, the more it costs to fix. Pair programming also forces skills transfer, creating better programmers. Like pair junior programmers, developers with senior developers. I do this all the time so that each one learns from the other's approach to a problem. They pick up tips and tricks that the other one uses, and it creates better programmers. You also get 2 sets of eyes on every line of code. You don't want code that only one person understands. Then that person goes on vacation, no one knows how to fix their code. Pair programming leads to better understanding of the code. More people understand the code well enough to fix and enhance it. In this video, you learn that social coding is done communally with public repositories, and all team members are encouraged to contribute. Pair programming results in higher quality code because defects are found earlier, costs are lowered, and there's a broader understanding of the code base. After watching this video, you'll be able to explain how the Git feature branch workflow supports social coding. Let's talk about guidelines for your repositories and workflow. Create a repository for every component, whether it's a microservice or something else you're building. Don't put multiple microservices in one repository. These are called monorepos and are frowned upon. People often create what we call a monorepo, which is a single repo with multiple microservices in it to make demonstrations easier. But this should not be done for production code. You don't want someone to have to check out a lot of code that they don't care about just to get to the code that they do care about. You want to have one component or microservice per repo. This is very important. Don't be afraid to have multiple repos. Create a new branch for every issue that you're working on. You don't want to have long-lived branches. I don't believe in having a development branch that all the work gets merged into and done. That's the old way of thinking. Branches are very lightweight in Git. There's a master branch and there are feature branches, and that's all there is. When you're done with the feature branch, you delete it. You don't get too attached to it because you delete it, you create a new one for the next issue you're working on. Use pull requests to merge your code back to master. The only way code should get into the master branch is through a pull request. A pull request gives an opportunity for other people to look at your code and review it. Never merge your own pull request. Just don't do it. You always want to have someone else on the team merge your pull request because every pull request is an opportunity to have a code review. Have them look at the code, make sure it makes sense to them, and then have them do the merge. This way you get 2 sets of eyes on all the code that's going into the repository. We call this the Git feature branch workflow, and here's how it works. Let's begin with the GitHub repo. You create your new repository for your component, or if you're contributing to someone else's component, you fork an existing repository. Next, you clone that down to your workstation, and it becomes your local repository. All of your changes will be made in this repository. Next, you create a branch to work on your feature. This can also be followed for bugs or other fixes. It's called a feature branch, but the idea is that it's the branch for the code that is associated with the GitHub issue that you're working on. When you're ready to submit your code back to the main project, or if you just want someone to review your code, your changes, and get feedback, you push your code to the remote branch. Finally, you create a pull request that your changes be reviewed. The pull request will be reviewed, and if the code is complete and meets the standards set out by the team, it'll be merged back into the master branch and become part of the original GitHub repository. In this video, you learned that creating a repository for every component, following the Git feature branch workflow, then creating branches and using pull requests is a good practice. After watching this video, you'll be able to explain working in small batches and recognize how single-piece flow yields faster feedback. Working in small batches is a concept from lean manufacturing. It's important in situations where fast feedback is required because it enables you to learn quickly from your decisions. You may be testing a hypothesis and you don't want to get too far before you know if it's going to work. Working in small batches allows you to experiment more in order to quickly gain insights. In contrast, working in large batches that take months to complete means you don't get feedback for months. Working in small batches also minimizes waste because you gain feedback faster and you don't waste time developing things your customer doesn't like. Using large batches, you may spend months developing something that isn't what the customer wanted. In keeping with DevOps practices and cross-functional teams and lightweight approaches, the best way to rapidly progress from development through test and operations into production in a matter of minutes is working in small batches. Let's take a look at an example of working in large batches versus small batches. Let's say I need to mail out 1,000 brochures, and the steps are I fold the brochures, insert the brochures into envelopes, seal the envelopes, and then stamp the envelopes with postage. We'll use this brochure example to compare large batch and small batch execution. Let's say that I'm going to process the first 1,000 brochures in batches of 50. These are large batches with 50 brochures in each batch. Assume that each step takes about 6 seconds to complete, so I can do about 10 steps per minute. I start with the first step, which is folding, and at 10 per minute, it takes me about 5 minutes to fold 50 of them. Then I move on to the next step. The next step is inserting them all, and I can do about 10 of them per minute, so it takes me 5 more minutes. Plus the 5 minutes before, now I'm 10 minutes into it. Once I have them all folded and I inserted, I move on to the next step, which is sealing them all. If I'm sealing 10 per minute, I could do another 50 and another 5 minutes, so I'm up to 15 minutes at this point in wall clock time. Finally, I get to the step 4, stamping, and it took me 16 minutes to get my first finished product. This is the first time that I have things that I can actually inspect to check the quality. What if the envelopes had no glue? It would be 11 minutes before I figure out that something went wrong. What if there's a typo in the brochure? I have to go all the way back to the beginning. So this is very wasteful working in these large batches. Now let's look at the same example with small batches using single piece flow. Again, assume each step takes about 6 seconds to complete. With single piece flow, I fold one and I put it into an envelope and I seal it and I put a stamp on it, and the first finished product is about 24 seconds. Now I can inspect it and see if it works, see if it's what I thought it was. And then let the rest of the flow continue if it was acceptable. I received fast feedback in only 24 seconds instead of 11 minutes with the large batch. Now, what if the envelopes had no glue? I'd find out in about 18 seconds. And if there was a typo in the brochure, after 24 seconds. It's very important that we don't work in large batches. We need fast feedback so that we can quickly pivot if we need to do something different. Working in small batches helps you implement other DevOps practices like continuous integration and continuous delivery. So how do you know if your batches are small enough? I would start with the size of your stories in your backlog. Are your application features decomposed in such a way as to support frequent releases? You have to ask yourself, how often are releases possible? Are there delays in release because the features are too large? Can features be completed in a sprint? If you have features that take several sprints, then your batches are too large. Ultimately, a feature should be small enough to be completed in a week or less. The features you build are one step towards a goal. Many people feel that only a completed goal is worth shipping, instead of thinking useful subsets that can be delivered in increments to gain feedback towards the ultimate goal. In this video, you learned that working in small batches means delivering something useful quickly, and using single-piece flow leads to faster feedback loops. After watching this video, you'll be able to define a minimum viable product and recognize how an MVP should be used to give the customer what they really want. Let's talk about a minimum viable product. First, let's understand what it is not, because there are some misconceptions that a minimum viable product is the same as phase 1 of a project or the first beta or something like that. This is not what a minimum viable product is. A minimum viable product is the minimal thing that you can do to test a value hypothesis and gain learning and understanding. You might say it's the cheapest thing you can do to prove a hypothesis. You can finish the first MVP, then you get the results, and move on to the second one, and so on. The difference between these two is that the first one is all about delivery. What am I going to deliver? But the second one is all about learning. What can I learn? What can I learn from putting out this MVP and getting feedback, and then maybe making the next one even better? So it's important at the end of each MVP, you decide whether to pivot or persevere. Should I pivot? That is, do something different, or persevere, continue doing what I'm doing. Let's look at an example. Here's a team that's developing a minimum viable product for a customer that wants a red car. And so in the first iteration, they deliver a wheel. And the customer's like, what am I going to do with a wheel? I can't do anything with this. Well, we're working iterations, they say. We're trying to be agile here. In the next iteration, we'll give you something more. And they give the customer a chassis. And the customer responds, I still can't do anything with this chassis. And then they give them a car with no steering wheel. And eventually, right, they get the whole car. Now the customer gets this coupe. And there's no feedback along the way. The team didn't know until the end whether the customer is going to like what they built or not. The team did not understand how to create a minimum viable product. They were just doing iterative development with no regard to whether each increment was useful or not. The second team understands the value of creating an MVP. At first, they give the customer a skateboard, and the customer says, what's this? I asked you for a car, you give me a skateboard. And the team said, no, wait. We're testing the color. How do you like that color red? Is that the color you want? The customer says, oh yeah, red's kind of cool. You know, it's really hard to steer though. So team says, no worries. In the next MVP, they give them a way to steer it. And the customer says, well, okay, you did give me a way to steer it, but I can't go very fast. I need a better form of locomotion. And so the team deals with that in the next MVP. The next iteration, they give them pedals to go faster. Somewhere along the way, while riding on that motorcycle, feeling the wind in their hair, the customer decides, I really want a convertible. In the first instance, the customer got exactly what they asked for months prior because the development team was just following a plan. But in the second instance, the customer got exactly what they desired because they were working iteratively and interactively with the development team. In the end, you develop something that's a little bit different, but it's closer to what the customer really wants. Giving the customer what they really want is the main purpose of delivering an MVP. A minimum viable product is a tool for learning. It's an experiment to explore the value proposition with your customer. And this experiment may fail, and that's okay, because failure leads to understanding. What did you learn from that failure? What did it teach you? What is the next experiment? What will you do different the next time? These are the questions that lead to gaining knowledge and understanding about what you're building. This is why we use MVPs in DevOps. In this video, you learned an MVP is the minimal thing that you can do to test your hypothesis. An MVP is not about delivery as much as learning. It's okay if the MVP fails. Make sure that you learn from it. After watching this video, you'll be able to define test-driven development, describe how TDD produces higher quality code, describe the red-green refactor workflow and describe the importance of TDD for DevOps. This is one of my favorite quotes. If it's worth building, it's worth testing. If it's not worth testing, why are you wasting your time working on it? Writing test cases is critical to proving that your code works as intended. What is test-driven development? Test-driven development, TDD, means that your test case drives the design and development of your code. You don't write code and then test it. You write the test cases first. You write tests for the code you wish you had, and then you write the code to make them pass. That may sound counterintuitive. How can I write test cases for code I haven't written yet? Well, how can you write a design for code you haven't written yet? You describe in the design how the code should behave, and then you write the code that behaves that way. TDD is no different. The test case describes the behavior that you want the code to have. This keeps you focused on the purpose of the code. That is, what's it supposed to do? You should absolutely be able to specify that before you start writing any code. Otherwise, how do you know what to write? This is also what keeps you focused on the clients that will call your code. I do a fair amount of back-end development. I love creating services for others to use. And one day, I'm creating what I'm sure would be an awesome service with a great application programming interface, right? A great API. I was down in the bowels of the code and I needed some information, and so I added as a parameter to the API. And then I needed something else, and I added as another parameter to the API. And eventually I needed more things, so I added those as parameters too. Now it's time to write some test cases for my code. And at the time, I wasn't following TDD. And when I started writing test cases, I suddenly realized I didn't have half the information that my parameters required. My beautiful API was horrible. How could it be this bad? Where had I gone wrong? Well, I didn't take the caller of my code into account because I wasn't following TDD. TDD gives you the caller's perspective. It allows you to explore how you would want to call the code before even writing it. It makes you consider, what do I know as a caller? What can I pass in and get back as an answer? Having this perspective is critical to writing good code. Code is of no use if no one can call it. So why don't developers write test cases? I get these excuses all the time. The first excuse, I already know my code works. Yes, but others who work on your code in the future won't know if they broke something, including the future you. I tell programmers, whenever you clone and pull from a repo, the first thing you do is run the test cases. How else do you know if you broke something or it was broken before you changed it? Test cases give you the baseline so that other people know that the code is still working. Another one is, I don't write broken code. Well, maybe you don't write broken code, but the environment is constantly churning underneath you. Vulnerabilities are being patched, new libraries are being upgraded, so your code may no longer work. Someone will say something like, we have a vulnerability in Apache Struts library. Can we update it on all our servers? And unless you have test cases to test your code and make sure that it works with a new version of that library, you probably shouldn't do that. And not doing that, as you may know from vulnerabilities that have happened at Equifax, could be catastrophic. You have to write test cases so that you can say with confidence, let me run the test suite. Yes, the new version of Struts works fine. Deploy it to production. My favorite excuse, I have no time. Well, this is the worst excuse because testing actually saves you time in the end. The time you spend writing a few test cases now is going to save you hours and hours of debugging later. Trust me on this one. You don't know who's going to use your code in the future, and you want to make sure your code is solid. TDD will keep you writing solid code. This is the TDD workflow. You write a failing test case, right, for the code you wish you had. Then you write just enough code to make it pass. It doesn't have to be perfect. It doesn't have to be pretty. It does have to make the test pass though, right? Then you refactor the code to make it better and increase the quality. And finally, you repeat the process. This is known as red-green refactor. Many of the testing tools follow this scheme. These tools output failing test cases in red, passing test cases in green, and this is how the red-green refactor got its name. So why is TDD important to DevOps? Well, first and foremost, it saves time when you're developing. As you add new features to the code or changes to existing features, right? This test case will quickly let you know if something broke. It allows you to code faster because you're more confident. You don't have to worry about if a change just broke your code. It broke something, right? When you refactor the code, you can move faster because you know the test cases will catch any changes in behavior. And TDD ensures that the code is working as you expected. If you write the test cases first to define the behavior you want, you will know that you have achieved that behavior when the tests pass. It also means that future changes don't break the code. Failing test cases will instantly alert you that someone has introduced something that broke the code. Finally, and most importantly, in order to create a DevOps pipeline, a CI/CD pipeline, all tests must be automated unless you want to push bugs to production faster. A lot of companies don't understand this. They want to automate using continuous integration and continuous delivery. Without automating their tests, unfortunately, you can't have a CI/CD pipeline without automating your tests. In this video, you learned that TDD means test case drives the design and development of code. TDD allows you to develop faster and with more confidence. The red-green refactor workflow has to do with red is fail, green is pass, and it increases the quality of the code. And in order to create a DevOps CI/CD pipeline, you must first automate your testing. After watching this video, you'll be able to define behavior-driven development, explain how BDD can drive customer expectations, and describe the key benefits of BDD. Behavior-driven development, as its name implies, focuses on the behavior of the system as observed from the outside in. This is different from test-driven development, which focuses on the minutia of how the system works inside. BDD is great for integration testing to see if all the components are behaving together. It forces you to think from the outside in. In other words, you implement only those behaviors that contribute most directly to business outcomes. One of the advantages of BDD is that it describes behaviors in a single notation which is directly accessible to domain experts, testers, developers, and customers. This improves communications across the team. If we compare BDD to TDD, we see that they're coming from the opposite directions. BDD describes the behavior of the system from the outside in. It's looking at the system as a consumer of it would, while TDD tests the functions of the system from the inside out. It's making sure that each component is working correctly, while BDD is making sure that they all work together at a higher level. Put another way, BDD is ensuring that you are building the right thing. Do you have the right set of capabilities in these behaviors? TDD is ensuring that you're building the thing right. Does each feature perform the task that it was intended to? The workflow starts with developers, testers, customers exploring the problem domain and collaborating to produce concrete examples that describe the behavior they want. They document these behaviors using a language known as Gherkin. It's a natural language representation that I'll talk about in a moment. Next, the team uses a BDD tool like Behave or Python or JBehave for Java or Cucumber for Ruby to run these examples as automated acceptance tests. As the team works on the solution, the BDD tool tells them which examples are implemented and working and warns them about ones that aren't. The BDD tool example like Behave or Python or JBehave for in a moment. Next, the team uses a BDD tool like Behave or Python or JBehave for Java or Cucumber for Ruby to run these examples as automated acceptance tests. As the team works on the solution, the BDD tool tells them which examples are implemented and working and warns them about ones that aren't. Before you know it, you have one document that is both the specification and the tests for your software. Gherkin is an easy-to-read natural language syntax that uses a familiar given, when, then syntax. Gherkin is easily understandable by both technical and non-technical people, and if you're wondering where the name Gherkin came from, the original tool that used this syntax was called Cucumber, and Gherkin is a pickle, and pickles are made from cucumbers. Tools have a funny way of producing funny names like that. Here's how the Gherkin syntax is used. Given some context, this is setting up the context or the precondition that sets the stage for the test. The purpose is to put the system in a known state before the user or external system starts interacting with it. When some event happens, this is the principal action or actions that describe what's being performed. This is what takes you from the initial state to the new observed state. Then some testable outcome or behavior is validated. Then is used to observe the outcomes. The observation should be related to the business value or the benefit of the feature. And is used for continuations. Given this and that, then this and that, and so on. It gives you a natural way of adding more context, events, or outcomes. Let's look at an example from a retail store. These are called feature files or feature documents, and you'll have one feature per document and many scenarios describing this feature. There's only one scenario in this example, but there could be certainly more to cover all the permutations. This feature is called returns go to stock, and this feature is described by the behavior of the system when a customer returns an item that they have purchased. Notice it uses the as a, I need, so that syntax. We use this in writing our user stories. You could think of this as a user story with acceptance criteria, where the acceptance criteria are the scenarios. This first scenario is called refunded items should be returned to stock. It reads as follows. Given that a customer previously bought a black sweater from me and I have 3 black sweaters in stock, when they return the black sweater for a refund, then I should have 4 black sweaters in stock. It's fairly straightforward. Your stakeholder should be able to look at this and say, yes, this is how return items to stock works. Or maybe, here's another way it could happen. Then you would document a new scenario for the returns go to stock feature. The point is, your stakeholders are actually helping you define the behavior of the system in a formal syntax that you can now execute test cases against. Let me say that again. You can actually execute test cases against this document. BDD tools like Behave and Cucumber can consume this document with no further editing or manipulation and execute test cases to prove that the system does indeed exhibit the behavior. That will put a smile on your developer's face. This is why I add acceptance criteria to every user story. I use the Gherkin syntax to define the acceptance criteria in the user stories that we write. There's no arguing over the definition of done at the end of the sprint. It's indisputable. The code either does or does not exhibit this behavior. BDD improves communication does not exhibit this behavior. It's indisputable. The code either does or does not exhibit this behavior. BDD improves communication among the team members, like developers, testers, product owners, and other stakeholders. It leads to more precise guidance on how the system should behave. It does this by providing a common syntax that's close to everyday language and has a shallower learning curve compared to TDD tools. Tools targeting the BDD approach generally afford the automatic generation of technical and user documentation from the BDD feature specification. Having a clear behavior visibly results in higher quality code, which reduces the cost of maintenance and eliminates the risk. Finally, with BDD acceptance criteria, you're already converted to user stories and test case scenarios before the actual development. Thus, automating test cases can start creating test process even before the product is tested. In this video, you learned that BDD focuses on the behavior of the system from the outside in. It looks at the system as a consumer of it. BDD uses an approachable syntax that everyone can understand. Key benefits of BDD include improving the communications, a common syntax, and acceptance criteria for user stories. After watching this video, you'll be able to recognize the impact of cloud-native microservices on application design, describe stateless microservices, and compare monolithic and microservices architectures. To fully leverage DevOps, you need to think differently about application design. You need to be thinking about cloud-native microservices. This image shows an application that's designed as a collection of small microservices, each one of these services independent of the others. Each service a particular domain of the application. You have gathered from the names of the services, this is a ride-sharing service. There are drivers and payments and trip management and notifications. These are all small services that are single-purpose based around a business domain. Notice the lines going from one service to the other. These are pointing to the REST APIs. No service is accessing another service's database. In fact, databases aren't even included in the picture. This is cloud-native design using microservices, a collection of stateless services. Cloud-native means born on the cloud, taking advantage of the horizontal scalability that the cloud has to offer. These services are following the guidelines set forth in the 12-Factor app, which describes how cloud-native applications should behave. This was first created back in 2011 by the Heroku team. Heroku was one of the first platforms as service implementations, and it paved the way for cloud-native platforms that we have today. Applications are designed as a collection of stateless microservices. Stateless doesn't mean the application doesn't have state. It means the services don't maintain the state, any hidden state, right? The state is persisted in a database. Each service maintains its own state in a separate database or persistent object store. Separation of state is important. If services were to share state, you wouldn't have microservices. You just have a distributed monolith. Resilience and horizontal scaling are achieved through deploying multiple instances, right? Once you break your application down into multiple independent services, you can scale them independently as needed. For example, I could scale up the notification service without scaling up the other services. This takes advantage of the seamless, endless horizontal scaling of the cloud platform. And instead of debugging and patching failing instances are just killed and respawned. We often use the expression that instances are cattle, not pets. Don't get too attached to your instances. We scale them out as needed, and we scale them back when not needed. And once you break up that application into lots of little microservices, you need to leverage DevOps pipelines to help manage continuous delivery of these services. The term microservice was coined by Martin Fowler and James Lewis. They said, microservice architecture style is an approach to developing a single application as a suite of small services, each running in its own process. These are not just threads. These are full processes running independently and communicating with lightweight mechanisms, often an HTTP resource. We now use REST APIs, these lightweight mechanisms. Fowler and Lewis went on to say, these services are built around business capabilities and independently deployable by fully automated deployment machinery. You saw that each service in the rideshare application was built around a business capability, such as driver service or passenger service and notification service. These services are independently deployable. For example, I can upgrade the notification service without redeploying everything else. It's particularly important that microservices enable everything to be independently deployed. How does this work with a monolith compared to working with microservices? Suppose you have a monolith that has calculations, copy capabilities, and to-dos. When you deploy this application, you have to deploy all the components together. We can split those out into multiple instances of independent microservices. If I need to increase my capacity to perform calculations, I can scale out those 3 instances and maybe make 10. I would not have to scale out the to-dos or the copy capabilities. It's very important to be able to scale them independently to make the best use of cloud resources. Each microservice would have its own database where it's keeping track of its own state. I could deploy them independently and change the database independently. I would only need to change and coordinate with my team to accomplish this because other services are using REST APIs to communicate. They're not selecting over each other's tables in the database. Suppose I'm working on an e-commerce website, which is a monolith, and I want to change the customer table. I would probably need to coordinate with the people on the order team and the shipping team, right, to change this customer table because they depend on it for orders and shipping. With a microservice, there's no need to coordinate with other teams because you're simply calling my REST API. You don't care what my table looks like. You come in through the API, I could change from using SQL database to a NoSQL database, and you would never know. You ask for customer data, I give you customer data. That is the one difference between a monolith and microservice architecture. With microservices, each service is loosely coupled and communicates through a REST API. In this video, you learned cloud-native architecture is a collection of independently deployable microservices. Stateless microservices each maintain their own state in a separate database or persistent object store. Microservices are loosely coupled services designed for scalability and communicate with APIs. After watching this video, you'll be able to recognize the importance of embracing failure, explain the importance of quick recovery from failure, describe how retry patterns, circuit breaker patterns, and bulkhead patterns help make applications resistant to failure, and describe chaos engineering. Once you design your application as a collection of stateless microservices, there are a lot of moving parts, which means there's a lot that can go wrong. Services will occasionally be slow to respond or even have outages, so you can't always rely on them being available when you need them. Hopefully these incidents are very short-lived, but you don't want your application failing just because a dependent service is running slow or there's a lot of network latency on a particular day. This is why you need to design for failure at the application level. Since failure is so you can't always rely on them being available when you need them. Hopefully into failure and describe chaos engineering. Once you design your application as a collection of stateless microservices, there are a lot of moving parts, which means there's a lot that can go wrong. Services will occasionally be slow to respond or even have outages, so you can't always rely on them being available when you need them. Hopefully these incidents are very short-lived, but you don't want your application failing just because a dependent service is running slow or there's a lot of network latency on a particular day. This is why you need to design for failure at the application level. Since failure is inevitable, you must build your software to be resistant to failure and scale horizontally. We must design for failure. We must embrace failure. Failure is the only constant. We must change our thinking from moving to how to avoid failure to how to identify failure when it happens and what to do to recover from it. This is one of the reasons why we move DevOps measurements from mean time to failure to mean time to recovery. It's not about trying not to fail. It's about making sure that when failure happens, and it will, you can recover quickly. Application failure is no longer purely an operational concern. It's a development concern as well. For the application to be resistant or resilient, developers need to build that resilience right in from the start. And because microservices are always making external calls to services that you don't control, these services become especially prone to problems. Plan to be throttled. You're going to pay for a certain level of quality of service from your backing services in the cloud, and they will hold you to that agreement. Let's say you pick a plan that allows 20 database reads per second. When you exceed that limit, the service is going to throttle you. You're going to get a 429 too-many requests error instead of a 200 OK, and you need to handle that. In the case you would retry, right, in this case, this logic needs to be in your application code. When you retry, you want to back off exponentially when it fails. The idea is to degrade gracefully. If you can, cache where appropriate so that you don't always have to make these remote calls to these services if the answer is not going to change. Now, there are a number of patterns that are important strategies, very important strategies to help you make applications resilient. I just want to go over a few of the popular ones. The first one is the retry pattern. This enables an application to handle transient failures when it tries to connect to a service or a network resource by transparently retrying and failing the operation. I've heard developers say, you must deploy the database before you start my service, right? Because it expects the database to be there when it starts. That is a fragile design, which isn't appropriate for cloud-native applications. If the database is not there, your application should wait patiently and then retry again. You must be able to connect and reconnect and fail to connect and connect again. That is how you design robust cloud-native microservices. The key here is the retry pattern, to back off exponentially and delay longer in between each try. So instead of trying like 10 times in a row and overwhelming the service, you retry, it fails. And you wait a second, you retry again. Then you wait 2 seconds. Then you wait 4 seconds. Then you wait 8 seconds. Each time you retry, you increase the wait time by some factor until all the retries have been exhausted, and then you return an error condition. This gives the backend service time to recover from whatever's causing the failure. It could be just a temporary network latency. The circuit breaker pattern is similar to the electrical circuit breakers in your home. You've probably experienced circuit breaker tripping in your house. You may have done something that exceeds the power limit of the circuit, and it causes the lights to go out. That's when you go down to the basement with a flashlight, right? And you reset the circuit breaker to turn the lights back on. Well, the circuit breaker pattern works in the same way. It's used to identify a problem and then do something about it to avoid cascading failures. A cascading failure is when one service is not available and it causes a cascade of other services to fail. With the circuit breaker pattern, you can avoid this by tripping the breaker and having an alternate path return something useful until the original service recovers and the breaker closes again. The way it works is that everything flows normally as long as the circuit breaker is closed. The circuit breaker is monitoring for failure up to a certain limit. Once it reaches that limit threshold, right, that certain threshold, the circuit breaker trips open and all further calls to the circuit breaker return with an error without even calling the protected service. And then after a timeout, it enters this half-open state where it tries to communicate with the service again. If it fails, it goes right back to open. But if it succeeds, it becomes fully closed again. The bulkhead pattern can be used to isolate failing services to limit the scope of a failure. This is a pattern where using separate thread pools can help to recover from a failed database connection by directing traffic to an alternate thread pool that's still active. Its name comes from the bulkhead design on a ship. Compartments that are below the waterline have walls called bulkheads between them, and if the hull is breached, only one compartment will fill with water. The bulkhead stops the water from affecting the other components, the other compartments, right, and sinking the ship. So using a bulkhead pattern isolates the consumers from the services as cascading failures by allowing them to preserve some functionality in the event of a service failure. Other services and features of the application continue to work. Finally, there's chaos engineering, otherwise known as monkey testing. While not a software design pattern, it's a good practice to prove that all your design patterns work as expected under failure. In chaos engineering, you deliberately kill services to see how other services are affected. Netflix has a suite of failure-inducing tools called the Simian Army. Chaos Monkey solely handles termination of random instances, and Netflix randomly kills things to see if they come up and whether the system will recover gracefully. You cannot know how something will respond in a failure in production until it actually fails in production, so Netflix does this on purpose. All of these patterns can help you build more robust software and respond gracefully to intermittent failures. In this video, you learn that failure is inevitable, so we design for failure rather than trying to avoid failure. Developers need to build in resilience to be able to recover quickly. Retry patterns work by retrying failed operations. Circuit breaker patterns are designed to avoid cascading failures. Bulkhead patterns can be used to isolate failing services. And chaos engineering is deliberately causing services to fail to see how other services are affected.